Hi viewers, welcome to the channel. Today we have another problem in our hands that was asked in GATE. This question is an interesting one because of so many reasons. First of all, I request all of you to read through the problem and try to solve on your own. Okay, I hope you have given it a try. Now, see, in this problem you have a disk. Disk is connected to the wall using a spring as shown here. And the spring is connected not to the center of the disk but at a location which is little d away from the center of the solid disk. So capital K is the stiffness of the spring and capital M is the mass of the disk, and polar moment of inertia, polar mass moment of inertia to be very specific. So the polar mass moment of inertia of the disk about the center is given as ma square by 2. One little bit of information. See, there are certain things that you should try to memorize, and this value for the polar moment of inertia of the disk belongs to that category. You are expected to know the polar moment of inertia values for certain things like a disk, for a road, about different axes. Okay. Now they are saying that the disk is free to roll without slipping on the ground. That particular assumption holds a lot of importance while we are solving this problem. So before I tell you what are the details of this particular assumption and in what ways this particular assumption helps us in solving problem, I will first take you to a crash course on planar dynamics, or I don't know, the dynamics of rigid bodies which are moving in a plane. Okay, it's a very crash course, it's not detailed, but I will just touch upon few basic concepts that will be very handy when we solve this particular problem. So I will start off my discussion by talking about what are the different types of rigid body motion that is possible within a plane. So the first is pure translation. So as shown over here, you have a block of mass, and let's say the mass is moving along this particular direction. There are a few important things that you need to remember about pure translation. The first thing is that every point on the rigid body will be having the same velocity. That is related to the kinematics. Now, if you want to write your equations of motion, considering the effect of external forces that is acting on the system, then you need Newton's second law. For a body undergoing pure translation, the equation of motion is pretty straightforward. So you sum up the forces along the x direction, that is sigma fx, then that should be equal to the mass of the body times agx. Ag is the mass center of the object. That's why the underscript capital G, the subscript and capital G. Again an x which denotes the acceleration of the mass center along the x direction. And if the body is having motion along the y direction also, then you can use this particular expression which will capture the acceleration of the object in the y direction. Make sense? That's pretty straightforward. Now coming to the second possible type of plane motion. It is pure rotation about a fixed axis. See, there are a few assumptions I'm telling you that this particular axis about which this road is rotating, that is not going to change with respect to time. This is a very important assumption because once you go to 3D dynamics and in situations where the axis of rotation will be continuously changing, in that scenario all these equations that I am using here won't be applicable. That's not something you need to bother at this particular point of time. But for the but for the time being, let's say this thing is rotating about this pivot point O, then velocity of the 2 points capital N capital B can be shown like this, where omega is the angular velocity with which it is rotating, and RA and RB are the distances from the pivot point to the points A and B respectively. I have written this from a magnitude perspective. I am not going into the vector notation of things. Now this was related to kinematics. Now once it comes to dynamics, if you want to write the equation of motion from a kinetics point of view for a body which is undergoing pure rotation about a pivot point O, these are the set of equations you need to use. See, again, I won't get into the details. You sum up the forces along the normal direction. So say this is the normal direction and this is the tangential direction. So you sum up the forces along the normal direction, that should be equal to mass times the normal acceleration of your mass center. The same holds true in the tangential direction also. Ft equal to summation of forces in the tangential direction is equal to mass times the acceleration in the tangential direction of the mass center. You would have, for a circular motion, you would have learned that an is r omega square and at is r alpha, where r is the radius of the point of interest and omega square is the angular velocity and alpha is the angular acceleration. I won't get into the details of those things again. These are to be taught as part of dynamics or your engineering mechanics. The third important equation which is of great relevance is when you sum the moments due to all these forces about the point O is the pivot point. See, you only have to consider the external forces acting on the system about the point O, then it will be equal to I0, where I0 is the polar mass moment of inertia of this particular object about the point O, times alpha, where alpha is the angular acceleration. So these are the equations of motion for a pure rotation case. Now what is general plane motion? See, general plane motion is something which involves both translation as well as rotation. So I have an example over here. Say I have a disk which is rolling over this particular surface, and let's say the surface is having sufficient amount of friction, so there is no slipping. No slipping means the contact point will be having a velocity of 0. Let's say this is the initial configuration and this is the final configuration. So at t equal to 0, you can say this was the configuration, and after a while, let's say t equal to t prime or t equal to t2, this thing has moved to this particular configuration. See, this particular configuration can be achieved by a combination of two motions. Of the two, the first one is a linear translation from this configuration to this configuration. See, it's like hypothetically we are saying this is the configuration with which we are starting our thought experiment, and this is the final configuration. See, this final configuration can be reached by two steps or in two steps. The first step is the linear translation from this point to this, and then I am saying let's assume that there is a pivot point here, and now I am rotating my disk about this particular pivot point, and see, here I am. Now the line AB is horizontal. So this is my final configuration. So this is general plane motion. In general plane motion involves both translation as well as rotation. So that is from a conceptual point of view. Now if you want to write equations of motion for a general plane, for an object which is undergoing general plane motion, it is comparatively you have a lot more equations to deal with, because motion is composed of both translation as well as rotation. So here are the three equations I have shown. First equation, you sum up the forces along the x direction, that will be equal to mass times the acceleration of the mass center along the x direction. The same holds true in the y direction also. And the third equation tells you, you have your mass center, you assume an axis. Let's say you have an axis that is passing perpendicular to the, see, we are talking about motion in plane. So let's say there is an axis that is passing through the mass center and it is perpendicular to the plane. Then I will have a particular mass moment of inertia for the rigid body about that axis. Let's call that is Ig, and alpha is the angular acceleration. So this will be equal to, this Ig times alpha will be equal to sum of all the moments about the point G due to the external forces. Make sense? So in a nutshell, equations for plane motion are relatively difficult. Sorry, equation for general plane motion is relatively difficult. And to our rescue, here comes the concept of instantaneous center. So the concept of instantaneous center will help us to reduce the complexity of the problem from that of a general plane motion to pure rotation. How is it? Again, I will explain the same with an example. So here I have a disk. This disk is rolling without slipping. See, this is very important assumption. When it is rolling without slipping, as I mentioned earlier, I can assume that this particular point is having zero velocity. Given that, using the concept of instantaneous center, this is called as the instantaneous center of zero velocity, because this point is having a zero velocity for the time being. So using this concept of instantaneous center, for that particular instant or for this particular instant or momentarily, I can assume that my disk is pivoted about this point. So this is pivoted about this point for that particular instant alone. For another instant, there will be another instantaneous center. So you can apply all these equations throughout the motion, but the instantaneous center will be different, but all equations will be applicable. So given that you can think of this thing undergoing a pure rotation about this pivot point, then equation of motion will boil down to this. You simply take the sum moments about this particular point, which is the instantaneous center, and it equate it to the product of IIC times alpha, where IIC is same as JIC, which is the polar mass moment of inertia of the system about the instantaneous center. It's actually about an axis that is perpendicular to the plane as well as passing through the instantaneous center. So that's it. So using the concept of instantaneous center, we can three equations are getting reduced to one. Initially there were three equations for general plane motion. Now using the concept of instantaneous center, I can bring it down to one single equation. A lot of introduction. Now let's go ahead and solve the problem. See, once you understand all this concept, then solving the problem won't take much of time. So this is the system which we are interested in. We are asked to compute the natural frequency. So the best way to compute the natural frequency is write the equation of motion that governs the system. So I am isolating the particular disk. Then I have external forces acting on the system, the frictional force, then the spring force. That weight and everything I am neglecting for the time being because they will be cancelled each other with the normal reaction. So I am not showing the normal reaction as well as the weight. It is implied that they will cancel each other. Now, see, I told you again for a particular instant I can think of this particular disk as undergoing a pure rotation about this point IC. Let's say then initially there was a line connecting the IC and this point as shown over here. Now I'm giving it slight disturbance by an amount theta. I'm making this line rotate by an amount theta. That means the spring will get extended by an amount as shown over here, which is A plus D times theta. Then the spring will exert a restoring force on the disk as shown here, K, which is the spring constant. A plus D times theta will give you the extension in the spring. Now I have everything in terms of theta. I have represented the amount of extension in the spring in terms of theta. Now I can go ahead and write the equation of motion. See, there won't be any moment due to the friction force because it is acting through the instantaneous center, so that won't cause any moment. J1c is the polar moment of inertia of the system about the instantaneous center. And why there is a minus sign? Because the spring force is restoring, it is not allowing, it is actually bringing the disk towards the opposite direction of theta. We defined this is the positive direction of theta. The spring force is trying to kind of pull this disk back. Well and good. Now the rest of the stuff is simply plug and check. You have formula for all these quantities, and in case if you were not remembering your parallel axis theorem, that will come handy when you compute the mass moment of inertia of the system about the instantaneous center. So that can be simply written as a summation of two things. The first term is the polar moment of inertia about the CG, and second term is mass times the distance between these 2 points. Things are pretty simple. Once you plug in all these things, then you will arrive at a value of natural frequency as shown over here. See, it's a good thing you always make sure dimensions are consistent. You can see here the numerator is having dimensions of stiffness times meter square, and the denominator is having dimensions of mass times m square. This m square will get cancelled, so I'm left with dimensions of k by dimensions of mass. That will definitely give me a radians per second, or a by second dimension, 1 by second dimension. So my equation, this is a quick check that I can always do to ensure that my equations are correct. Thanks for watching.